Okay, the change of variables technique will be used here to evaluate this definite integral. So we have limits of integration here from 0 to 2. So this is basically the substitution method, which we've already covered, just that we have to do one extra step. We have to change these limits of integration here as well. So let me show you that. The substitution we're going to make is u is equal to x cubed plus 1. So we differentiate with respect to x, and we get du over dx equals 3x squared. But I'm going to multiply both sides by dx anyway. So here we go, and then divide by 3, and we get 1/3 du equals x squared dx. We have the dx here, and we have the x squared here, so I can make my substitution be 1/3 du. The x cubed plus 1 is equal to u, so I'll change this to square root of u. Square root of u I'll rewrite as u to the half. So we have one more step here. We have to change the limits of integration here because now we changed it to u. So these are x from x equals 0 to x equals 2. So we go back here, and let's start with x equals 0. When x equals 0, u equals 1. So the lower limit here is 1. The upper limit, that's when x equals 2. 2 cubed plus 1 equals 9. If you hear the phone in the background, I hope someone picks that up. Uh, so we have the new limits here. Let's use the antiderivative rule, the power rule here. 1/3, add 1 to the exponent. 1/2 plus 1 is 3/2, and then you divide by that exponent, so it's flip and multiply, that's 2/3, and we're going to evaluate that from 1 to 9. 1/3 times 2/3 is 2/9, u to the 3/2 evaluated from 1 to 9. Okay, so this becomes 2 over 9, u is equal to 9 to the 3/2 minus 2/9 1 to the 3/2. So you could use a calculator here if you want, but you don't really have to. 9 to the half first is 3, and then 3 cubed is 27. 27 divided by 9 is 3, then times 2 is 6. Moving over here, 1 to the 3/2 is just 1. This is minus 2/9. So this becomes 6 minus 2/9 is just 5 and 7/9. Okay, this is a pretty ugly looking indefinite integral. We're going to let u equal tan cubed theta. Du will equal 3 tan squared theta multiplied by secant squared theta, and I'll multiply both sides by d theta, and I'll get this. Let me divide by 3 tan squared, so 1 over 3 tan squared theta du is equal to secant squared theta d theta. Okay, so I have a secant squared d theta here. I'm going to replace that with 1 over 3 tan squared theta du. And the 1/3 I'll write out here. Du over here. Now I still have this tan cubed here, but I have to divide by tan squared. So tan cubed divided by tan squared is tan. So I can write a tan in here, but that doesn't change the theta. It's still tan theta. So I go back up here, and tan theta is going to equal u, or the cube root of u, which I'll write as 1/3. So u to the 1/3. So I'll replace this with u to the 1/3. Okay, now the limits of integrations need to be changed. So here I'll use this substitution. U is equal to tan cubed. I'm just going to rewrite it as tan theta all cubed. So the lower limit of integration to 0 here will be tan 0 all cubed. Now tan of 0 is 0, so cubing that gives you 0, so the lower limit doesn't change, it's still 0. The upper limit of pi over 4, tan of pi over 4, that's a special angle, that's the 45-degree angle, and that's going to be 1. Tan of pi over 4 is 1, cubed is 1, cubed is 1. So that's from 0 to 1. Okay, so the antiderivative of u to the 1/3, we add 1 to the exponent, we get 4/3, and then we divide by that exponent, so flip and multiply, we get 3 over 4, evaluated from 0 to 1. Let's simplify. 1/3 times 3/4 is 1/4 u to the 4/3, evaluated from 0 to 1. That's 1/4 1 to the 4/3 minus 1/4 0 to the 4/3. And 1 to the 4/3 is just 1 times 1/4 is 1/4. 0 to the 4/3 is 0 times 1/4. Wipes that out, and we're left with the final answer, 1 over 4. Okay, our final example here, an application problem. We want to figure out the area below y equals x over x squared plus 1 from 1 to 3. So let's write that as a definite integral. That area is going to equal from the integral of 1 to 3 of x over x squared plus 1 dx. Okay, so a substitution we're going to make here, we'll let u equal x squared plus 1. So du will equal 2x dx, and 1/2 of du will equal x dx. So we have the x dx here, so we'll replace that with 1/2 du. And the x squared plus 1 will get replaced with u. So let's figure out our limits, our new limits of integration here. When x equals 1, what does u equal? Well, when we substitute 1 in here, we get 1 squared plus 1, which is 2. When x equals 3, substitute 3 in here, we get 3 squared plus 1 is 10. Okay, so the antiderivative of 1 over u is ln u, or ln absolute value of u. And we're going to evaluate that from 2 to 10. Let's make our substitution here. We get 1/2 ln of 10, and I'm dropping the absolute values here because 10 is positive, not necessary to write absolute value, minus 1/2 of ln 2. Okay, so there's your answer, but let's keep on simplifying here. 1/2 is a common factor, so this would be ln 10 minus ln 2. And we know that the difference of logs is equivalent to 10 divided by the ln of 10 divided by 2. So this is 1/2 of ln 5. And there's another property of lns. This 1/2 can be written as an exponent of 5. So that'll be ln of 5 to the half, which we can write as ln square root of 5. And that's your final answer.